Welcome back. It has been seconds since I have seen the computer, but it may have been days since you've seen me. I'm Amy Fuchsteiner. This is Math with Business Applications, and we're about to continue on with our Unit 8 information, where we're doing annuities, sinking funds, and amortizations. Today we're going to be covering Chapter 12, Section 2. This will be the present value of ordinary annuities. In other words, how much do I need to put away today so that I have enough to receive payments of X amount of dollars in the future? So, for the present value of an ordinary annuity, Chapter 12, Section 2, our goals are to understand the purpose of the present value of an ordinary annuity, who uses it, when do they use it. We want you to be able to calculate the present value of the ordinary annuity using two different methods. The first being the ordinary annuity present value table. This means, as we have done before, being able to calculate the interest rate per period, the total number of compounds, and to identify the payment amount. We're going to be using the present value formula as well. Once again, this is not a simplistic formula. This is going to cause, you're going to need to know how to work that calculator, is what I'm trying to say. You're going to need to know how to work that calculator, and if you don't, please reach out for help. So we're going to then also, as we have before, want you to be able to separate the amount of money that was initially invested from the future value or from the amount actually totaled up by the payments and discover or determine the interest earned on that account. Right? The present value of an ordinary annuity is the idea that you can deposit a large amount of money in a single lump sum at one time, today, now, in the present. And over time, you are going to pay yourself out of that money. So over time, you are going to collect regular payments from that account. Those payments will occur to yourself or to another person, I guess, on a regular basis. They will be consistent in the amount and in the time. Eventually, your last payment will drain the account so that its balance is zero. Okay? So what's happening is maybe you put $4,000 away in an account, and then every month you're able to take $400 out of that account. So there's $4,000, and at the end of the first month, I'm going to take $400 out. That leaves $3,600 in that account. Right? The second month, that account of $3,600 is going to earn interest. So a little bit of money will go back into that account. And at the end of month 2, there might be $3,615 in that account. But at the end of month 2, I'm going to take out another $400. So now there's $3,215 in that account. But I'm also going to earn a little bit of interest in the next month, maybe $14. So every month I'm taking a consistent amount out, but an inconsistent amount based on interest is going to go back into that account, right? Which means I actually need to put away less money than the total of all the money I'm collecting, right? Okay. And the last withdrawal should zero out the account. There should be nothing left in the end. So how much is that present value? We're going to discover it two ways. One of the things we're going to use is our present value table. And that table, again, here, future values on the top. We want the present value on the bottom, or tables 12-2 in your textbook. I want to say it's pages 382 and 383 if you have a physical copy of the textbook. All right. So what do? Well, it's a table like the other ones before it. So we're going to find the interest per period. That's the I, or the yearly interest rate divided by the number of periods in a year. We're going to find N, the total number of compounding periods. That's the number of compounding periods in 1 year times the number of years. And we're going to use those two to locate the table factor on the ordinary annuity present value table. We want to make sure we're looking at the present value table. Again, pages 383 and 382 and 383 in your textbook, table 12-2 as you're doing your web assign homework or in your eText. And then again, there is a printable version of this in the learning module for this week. All right, once you have that table factor, you just need to multiply the payment by that present value annuity table factor in order to get the present value or the amount that needed to be deposited today. This little snippet is a snippet of the present value table. Notice that it starts with every number being less than 1. Because if I want to collect $400, say 10 times, that would be $4,000. I actually need to put away less than $4,000. So less than the number. Whatever our compounding periods are, the number we get off of the present value table should be less than the total number of compounding periods that we have in the length of the annuity, right? Couple of examples using this annuities table. A theater wants $20,000 available at the end of each 6-month theater season for regular maintenance due to use. How much must be deposited now if they have 8% interest compounded annually to yield this annuity payment over the next 6 years? So they want to collect 6 payments, or they want to be able to pay themselves 6 payments of $20,000. That's $120,000. Wait, how many times a year? At the end of each 6 month. Oh, so twice a year. So they want to be able to collect 12 $20,000 payments. That's 240. That's nearly $250,000. All right. So as they're doing that, though, if they're able to put a lump sum amount, it's going to earn interest. And so they won't actually need to put away $240,000. They'll need to put away less than that. We're going to use the present value table to figure out how much less. So here we go. We've got 8% interest. We've got payments of $20,000. Every 6 months is semi-annually or 2 times a year. So we're going to find our I value, which is 8% interest, twice a year, so 4% per period. Total number of compounds is twice a year for 6 years, or 12. I had to figure that out a couple of times. So our table factor that we're looking up is 4% and 12 periods. This is just a snippet of that 12-2 present value table. Notice that it starts with a number less than 1, 0.99, still less than 1. So I know I'm on the present value because I should need less. So I'm going to go down the 4% column, and then I'm going to go over to 12 compounding periods. Their intersection gets me 9.38507. So that's my present value table factor. That means in order to calculate out my present value, I need my table factor, which is the 9.38507, times the annuity payment of $20,000. This is essentially saying that even though I want to collect that annuity 12 times, the number of compounds, I only need to put away 9.3 times, or $187,701.40 if I'm using the correct number of decimal places. So how much will the theater be taking from the account over the next 6 years? Well, they're going to take all of it. They're going to take all of it, but if they're able to put away $187,701 today, they're going to keep earning interest on that over the next 6 years. And that interest will account for some of that $240. They won't need to put it all away. So the theater is going to collect $20,000 from this account 2 times a year for the next 6 years, or $240,000. So they'll be able to withdraw $240,000 over the next 6 years. If they've only put $187,701.40 into this account, where is that additional money coming from? That's the interest. The interest will be the difference between the amount that they're able to withdraw and the actual investment that was put into this lump sum. So we're going to take the $240,000 that they will be withdrawing and subtract from it the $187,701.40 to get $52,298.60. That's the interest on this account. You got it? They can put less away because they're not withdrawing all at once. They're going to let it earn interest while they're withdrawing the money. That means they can put less away to start. Second example. An insurance settlement will pay Barb $1,200 a month for the next 3 years. If the insurance company is able to invest at 6% compounded monthly, how much should they put down today to cover all their withdrawals? So rather than trying to come up with the money every month to pay Barb the $1,200, they're going to earmark a fund for Barb. And they're going to put that amount aside today to make sure that it's there and that they have it, and they're not going to touch it. And they're going to let that money earn interest, so that some of that interest pays Barb's $1,200. We're going to use the present value of the annuity to determine how much they have to put away today so that they can cover all of Barb's payments. All right? We need to do this using the table. So we're going to do I and N. Our interest is going to be the 6% compounded monthly, or 12 times. That's 0.5%. Total number of compounds would be 3 years and 12 times a year, so that's going to be 36. Our table factor for 0.5% and 36 periods would go down the 1/2 column and across the 36 to get 12. What is that? That's 37.87102. Now, remember, we've got 36 compounds. This number should be less than 36. We shouldn't have to put it away 36 times. We should be able to put away less than 36 times. So we're going to take that annuity payment of $1,200 and multiply it by the 32.87102 to get $39,445.22. If they want to pay Barb the $1,200 for the next 3 years, they need to be able to put away $39,445.22 today. And if they can do that, then they can set it and forget it, right? Now, how much is Barb going to receive over those next 3 years? Well, Barb's going to get $1,200, 12 times a year for the next 3 years. So Barb is actually going to collect $43,200. That's more than the amount of money they put away. And that's okay, because they're going to put that $39,000 away and it's going to earn interest. And that's going to offset that first $1,200 that they pay Barb. Right? How much interest are they going to be able to earn over the next 3 years? Or how much of the payments will they be able to offset? That's the interest. So we're going to take the amount that Barb is actually going to be able to get paid or withdrawn, which is $43,200. And we're going to subtract from it the amount of their lump sum investment, which is $39,445.22. This gives us interest of $3,754.78. How we doing? You doing okay with this? Do you need a stretch? Okay. I do. I'm having some issues. All right. Let's try. I do have a practice table here. Oh, and it looks like I've got a blue circle for whatever reason. This is the present value ordinary annuity table. We've got an annuity payment of $2,000 compounded yearly or paid yearly for 20 years at 7%, compounded annually. So we're going to find the table factor and the present value. I'm not going to do the interest on this one. I went through that in the previous two examples. All right, so our I value would be 7%. 7% divided by once a year would give me 7%. Total number of compounds would be 20 years once a year, or 20. So we're going to be looking up 7% for 20 periods on the present value table. Well, that's why I got a circle there. Okay, so the present value table, the starting number should be less than 1. It is 0.99502 because we should put away less money than we need in the present. I'm going to go down the column for 7% and across the column for 20. I'm coming from the back side this time. This gives me a table factor of 10.59401. 10.59401, yep. So that means in order to find, oh, this is kind of good, right? Because we're going to collect $2,000 20 times, but we really only need to put away enough for 10 and a half times. So we're going to do 2,000 times 10.59401 to get $21,188.02. It's kind of nice. All right, I'm just going to take a minute here and click through the next couple of examples. Please feel free to pull out pencil, paper, and calculator and your 12-2 table to make sure that you can do these independently before you start your homework. If you notice any mistakes, please don't hesitate to shoot me an email and let me know what they were. All right, present value of an annuity, we're going to do the formula. This is the second part of today's presentation, is the ability to do the formula. So the present value annuity formula is another sort of involved one. Couple of things here. PV, or the present value, is the lump sum of the money that's going to be dropped into an account so that regular payments can be siphoned off of those accounts. For this present value of an annuity formula, you are determining the lump sum. You will know the payment. So you are aware of what the payment should be, and you are going to find the lump sum amount that needs to be put away. The I is the interest per period. It is the same. The N value is the total number of compounds. In this formula, that N is negative. Please be careful of the negative. You will also notice that this is 1 minus the 1 plus I to the negative N and not minus 1. There are a few small tweaks to the formula that make it different but cause huge differences in your answers. All right? So when you do the formula here, again, as before, if you need calculator help, contact myself, your instructor, embedded support, or the Math Center. We will all help you one-on-one with your calculator and this formula. We will find a way to get it in to your calculator that works for you. All right? Okay, so make sure, as before, that you know what your variables are. Be sure that you can identify the payment amount, the rate, the compounds, and the time, and that you can find your I and your N values. Make sure you are aware and know your calculator. Know that ANS is your last calculation. Know that the chevron key, or Y to the X, will get you to your power. All right. You may also find it to be incredibly helpful to know how to use your store or recall or memory key. Lastly, use the order of operations. Add your I plus 1. Take that number to the negative N power. Be sure you're using your negative key and not the subtraction key. I cannot tell you how many people use the subtraction key instead of the negative. Know where your negative key is. All right. You're going to subtract that answer from 1. That may mean you have to use 1 minus second equals to get 1 minus answer. We're going to divide that then by I and multiply that final brick answer by the payment. An example of how that goes. Here we have Mike, who wants to have $500 during each 3-month period for the next 10 years. So he wants to put away a lump sum. so that he can pull $500 every 3 months off of that for the next 10 years. Why? I don't know. Maybe he is just looking at retirement and he wants an extra $500 every 3 months so he can travel. Maybe he's got a bill he wants to pay. I don't know. But he wants to have $500 every quarter, each 3-month period, over the next 10 years. And he has the availability, the funds to put a lump sum away so that he can pull off of that account for that time. Mike's bank is currently offering 8% compounded quarterly. How much does he have to deposit today if he wants his payments, if he wants that amount of payments at the end of each 3 months, right? So we are determining the present value. We know the payments, and those payments are going into the future. So we are finding the present value. Our interest per period is the 8% divided by 4 because it's every 3 months or quarterly, so 0.02. Keep in mind, as before, when you're putting it into the formula, you want to make sure you're using your percent as a decimal. This is not just a straight 2%. I need to convert that 2% to a decimal. My preference is to convert it to a percent at the very beginning so I don't forget, but you do what works for you. It just needs to be a decimal. My N value is 4 times a year for 10 years or 40 different compounds. The regular withdrawal amount is going to be $500. So that's my payment, is that $500. The formula is that the present value is equal to the payment times square brackets, just another way of doing parentheses. In the numerator, I have 1 minus 1 plus I to the negative nth power. And then I'm going to divide all of that by the interest per period again. Using my substitutions, this will look like 500 times, big parentheses, 1 minus 1 plus 0.02 to the negative 40th power divided by 0.02 again. I am going to do what's in parentheses, 1 plus 0.02 to the negative 40th power first. So I'll have 500 times 1 minus 0.452890415. Divide that by 0.02, or 500 times 0.547109585 divided by 0.02. Now, I'm going to find what's in those square brackets first. 0.054109585 divided by 0.02 gets me 27.35547,924, which I'm going to multiply by 500 to get $13,677.74. Mike is going to put those $13,677.74 away into an account today. Every 3 months into the future, he's going to pull $500 from that account. He will do this for the next 10 years. Keeping in mind that while Mike is taking his money out, interest is being added in. Mike will be able to continue to withdraw even after his original $13,677.74 is gone. That additional money will help us to determine the interest. So how much money will Mike be able to take from this account? Mike is going to take $500 4 times a year for the next 10 years. That's going to be a total of $20,000. Mike is going to withdraw a total of $20,000 from this account. Keeping in mind that Mike has only put $13,677.74 into the account, where are we coming up with that extra money? Well, because of time, we can take the total amount that's withdrawn, the $20,000, and subtract Mike's original investment from it, the $13,677.74, or $6,322.26, and that's what's going to be earned in interest. That interest makes it possible for Mike to put less money in than he's going to be taking out. Carrie would like to set up an annuity of $2,000 $2,250 semi-annually for 5 years to help her daughter pay for college. How much should she deposit now at 4.2% interest compounded semi-annually in order to accomplish this goal? So in this problem, we have an example where Carrie has a daughter that's going to college. Carrie, has the funds now to put some money away so that her daughter can draw on that over the next 5 years as she works her way through college. Carrie has the availability of 4.2% interest compounded semi-annually. So we need to find her interest rate per period, which is the 0.042% as a decimal, divided by 2 because we're compounding semi-annually, or 0.021. Total number of compounds is twice a year for 5 years, or 10 total compounds. And the regular withdrawal payment is $2,250. Using the formula, the payment times big block of parentheses, 1 minus 1 plus I to the negative n power, divide that by I. Once I know what that is, I'm going to multiply it by the payment. Using the using substitution, I want to do that first. Sorry, I'm ahead of myself. We're going to take the payment of $2,250 times 1 minus parentheses 1 plus 0.021 to the negative 10th power, that's my n, divide by 0.021, or $2,250 times 1 minus 0.8123488867 divided by 0.021, or 2,250 times 0.18765111133 divided by 0.021, or $2,250 times 8.935768234. Do you see that 8.9? That number should be less than the number of compounding periods. So because we're looking at the present value, because the present value should be less than the total amount that Carrie is able to withdraw, I'm looking at multiplying that 2250 by less than 10. So this at least gives me a clue that I'm in the ballpark. Even if my number is off because of a calculator error, I still am sort of in the ballpark. So I've got 22,050 times the 8.937,357,68234, or $20,105.48. So we know that if Carrie wants to be able to withdraw $2,250 twice a year for the next 5 years, she has to have just over $20,000 to put away today. Now, how much is Carrie actually going to receive from this account? Well, she's going to take $2,250 out of this account twice a year for 10 years. I'm sorry, twice a year for 5 years, or 10 times. This is $22,500. So Carrie's daughter will withdraw a total of $22,500 from this account. Notice that's not how much she put in. She only put $20,105.48 into the account. The difference between what she's able to withdraw and what she puts into the account is the interest. So we're going to take $22,250 and subtract the $20,105.48 to get $2,394.52. That would be the interest on this account. Now, notice, Carrie's going to put in $20,105.48 into an account today, in the present. That's how much she needs in the present. Every 6 months, she's going to take $2,250 out of that account. She's going to do that for 5 years. Keeping in mind that while Carrie is taking money out of this account, interest is being accrued and deposited into the account. This is going to offset the withdrawals and allow Carrie to withdraw more money than she actually puts into the account. I have, as I've had before, a practice table so that you can take the formula. There we go. Payment times 1 minus 1 plus I to the negative n over I. And practice on your calculator with that. This practice table is available in the PowerPoint if you would rather just sort of cut it off now and go do that. I will also go through it here. So our first payment is $280. We're going to do that monthly for 5 years at 3.6% interest. So our I value is the 0.036 divided by 12, or 0.003. Total number of compounds is 12 times a year for 5 years, or 60. The payment amount is $280. So they want to be able to withdraw $280 monthly over the next 5 years at 3.6% interest. So our present value, the amount of money that needs to be deposited today, would be found by taking 280 times 1 plus 1, or 1 minus, and then in parentheses 1 plus 0.003 to the negative 60th. So you want to do that part first, the 1 plus 0.003 to the negative 60th power. Got that number? Now do 1 minus that number. Divide that by 0.003. That should give you a number that is less than 60. It should be less than the number of compounds because this is present value. Take that number times the 280. You should get $11,102.82. The second example has a payment of $850, compounding monthly, so we're going to take it every month. We have 2.4% interest rate, compounded monthly, because it has to be the same. This is a simple annuity for the next 10 years. So finding our I and our N, our interest per period would be the 0.024 divided by 12. Total number of periods would be 12 times a year for 10 years, or 120. The payment that they would like to receive is $850. So we're trying to figure out how much money do we need to put away today so that we can collect $850 every month for the next 10 years. Does it seem like that should be enough? Because it probably should be. All right, making the substitutions into the formula. 850 times, we want to do that whole fraction part first. 1 minus 1 plus 0.002 to the negative 1/20th. Divide that by 0.002. We're going to start with the parentheses. With your calculator, we're going to do 1 plus 0.002 to the negative 120th power. So 1.002 to the negative 120th power. You got that number? Now do 1 minus that number. You can store it. You can do second answer. You can retype if you have to. Now take that number and divide it by 0.002. This number, this answer, should be less than 120. It should be less than 120. Now multiply that by 850, and you should get $90,603.02. I'm going to click through the next 3 here. So I'm going to go silent. All right, I would say, as I did with the last presentation, that the 7% weekly can be either done as a 0.07 over 52 and keep that particular calculation, or you may choose to store that number in your calculator or write it all out, but please do not round it to some nice number, right? Keep as many decimal places as you can. It's a pain, but you want the whole number. The summary for the present value of an annuity. This is an ordinary annuity in present value, keeping in mind that this is a lump sum that is deposited now, and we take regular equal withdrawals. Our payment or withdrawal amount is known. The lump sum is not. We are finding the lump sum. Because this is an ordinary annuity, it is done at the end of each period. And the number of payments that you take will be the same as the total number of periods for the annuity. The total value of the payments should always be greater than the lump sum. The payments that are taken out will always drain the account so that the ending balance is 0. The interest earned will be the difference between the present value of the account and the total of all of the payments, or the payments times the number of compounds. Some common ordinary annuities are loans and bonds. Our table factor can be found as a cross-section of I and N, and the formula is going to be the present value is equal to the payment times, big parentheses, 1 minus 1 plus I to the negative nth power, all of that divided by I. The present value of an ordinary annuity, can you understand the purpose of the present value of an ordinary annuity? Do you know who might use it and when? Could you give an example of that if you had to? Can you calculate the present value of an ordinary annuity using a table? That means, can you find the interest rate per period, the number of compounding periods, and can you identify the payment needed? Are you able to use the present value formula successfully to calculate the present value of an annuity? This would include being able to identify the various parts of the formula and to successfully navigate your calculator to determine that future value. And as we have discussed in previous sections, we want you to be able to separate the amount that was initially invested with the interest earned and the total amount of the payments. There is extra practice in your eText book. This is chapter 12, section 2. And again, because we are sticking with just ordinary annuities, you are going to want to be careful about the problems you do in those review exercises. Please stick to 1 through 5, 11, 13, 15, 17 through 19, and 23. There is extra practice in your physical textbook. I believe those are pages 385 to 387. If the pages are wrong, it's still the review at the end of section 2 from chapter 12. As with the last presentation and all presentations so far this term, there is a graded assignment available on WebAssign. It is actually called chapter 12, section 2. I will need to fix that. Pen, chapter 12, section 2. There we go. All right. As always, if you need help, please feel free to contact myself. Make an appointment with your embedded support tutor. Contact the Math Center. They are drop-in open until at least 9 o'clock most evenings, or any other support you may have. We want to see you succeed. This is the last week. Please reach out if you need help. Thank you.